Welcome back. Today, we're diving deep into the backbone of big data, Apache Hadoop. In an era where data grows exponentially, traditional systems just can't keep up. We're going to explore how this open-source framework enables distributed storage and processing at scale. Our agenda is packed. We'll break down the HDFS architecture, master the MapReduce workflow, look at the evolution of Yarn, and even walk through some practical labs like word count. Let's get started. First, let's look at how Hadoop stores massive amounts of data using the Hadoop Distributed File System, or HDFS. HDFS operates on a master-slave design. At the top, we have the name node. Think of this as the brain. It manages the file system namespace and knows exactly where every piece of data is stored, but it never actually stores the user data itself. Underneath, we have DataNodes, which do the heavy lifting by storing the actual blocks. HDFS is built for reliability. Files are split into large 128 MB blocks to minimize seek time. To prevent data loss, each block is replicated 3 times across different nodes. If a node fails, the name node detects it through missing heartbeats and automatically triggers a re-replication. This is fault tolerance at its finest. Now that we've stored the data, how do we process it? We use MapReduce, a parallel computation framework based on a simple principle: move the compute to the data. Instead of moving a massive dataset across a congested network, Hadoop sends the small snippet of code to the node where the data already lives. The process happens in 4 steps. Input: large files are split into blocks. Map phase: raw data is transformed into intermediate key-value pairs. Shuffle and sort: the system groups these values by key. Reduce phase: these values are aggregated into a final result and written back to HDFS. It's essentially a divide and conquer strategy for massive datasets. Hadoop has evolved significantly. In the early days, MapReduce 1, MR1, had major limitations. It relied on a job tracker that was a single point of failure and used static slots that led to inefficient resource usage. Enter Yarn, or yet another resource negotiator. Yarn introduced a decoupled architecture, separating resource management from job scheduling. It replaced those rigid slots with dynamic containers that allocate CPU and RAM based on actual needs. Most importantly, Yarn turned Hadoop into a data operating system, allowing other engines like Spark, Flink, and HBase to run natively on the same cluster. Depending on where you are in your development cycle, you'll use different cluster modes. Standalone mode is for debugging. It runs as a single Java process on your local machine and uses your local file system instead of HDFS. Pseudo-Distributed mode is great for functional testing. All daemons run on one machine, but they simulate a real HDFS environment. Fully distributed mode is the production standard. This involves a cluster of multiple physical machines, providing true scalability and high availability. To wrap up, let's look at a practical lab. In standalone mode, we can execute jobs using the Hadoop jar command. A common starting point is the grep example, which uses regex to find and count string matches in XML config files. Then there's the hello world of Hadoop word count. This involves compiling a Java program, packaging it into a jar, and running it to count unique word frequencies. One critical tip: Hadoop is picky. If your output directory already exists, the job will fail, so always ensure you're pointing to a new path or delete the old one first. That covers the essentials of the Hadoop ecosystem. From storage with HDFS to resource management with Yarn, you now have the foundation to handle data at scale. Would you like me to walk you through the specific Java code for the word count mapper and reducer next?